Hi everyone. Alright, this is part 2 of the podcast in revisiting skills necessary for success in our unit on RedOx. Let's continue. Alright, number 12. Which metal is more active than H2? We're looking at silver, gold, copper, and lead. Which one is more active? For that, we must look at our table J, which is an activity series, and we will identify each of them. And here is H2 right there. There's silver, gold, and copper. Right then and there, 3 of them are below it, so you must think, wow, 3 of them are below it. It must be the other one. And which one was it mentioned? Oh, right there, lead. So which one of these is not like the other? Which one does not belong? That is if you do forget the rule. And the rule is the element that is above the one mentioned is the more active. In fact, it says it right here. It is more active. So the answer for this one will be lead. Let me get this off the screen and let's choose it. There we go. It was choice number 4. All right, question 13. Now this one might take a while and this one might get a little bit confusing, so please pause it, rewind it, go over it many times because I'm going to go through it very carefully with you. The question reads, which statement describes where the oxidation and reduction half reactions occur in an operating electrochemical cell? Let me bring forth a picture of an electrochemical cell. Here it is. Now let's start breaking down to understand it. Where is the oxidation and reduction going to take place? Now in this picture we have aluminum, which is this electrode right here that I'm scribbling in. And it's noted right here. 2 aluminums, in fact, help balance the equation for reasons we do not need to get into at this moment. But we do need to note that the aluminum, when it is uncombined, has an oxidation number of 0. On the right side, we have nickel, and it's this electrode I am scribbling in. It is noted right down here on the product side, and it also has an oxidation number of 0. Now, if we inspect the equation below, we will see that the aluminum has an oxidation number of 0, and when it lands on the product side, it's a +3. Now, there are 2 aluminums on the left, 2 aluminums on the right. The 2 aluminums on the right are +3, so they must be giving up 6 electrons to go from this to this. Which also means that, let me choose a different color, that this nickel, which is +2, but we have 3 of them, is a +6 on the left. On the right, it is 0. Well, what must be happening? It must be acquiring 6 electrons to have 3 nickels that now have an oxidation number of 0. Now, where did it get those electrons? Well, it got them from the aluminum. So we could actually almost do this, saying that there were electrons diverted to the nickel. All right, so let's make some sense of this. The aluminum loses electrons to the nickel, and the only way that that can happen is if it goes through this wire when this switch is closed. All right, so the aluminum is going to lose electrons to the nickel. Now, in this form of chemistry, we call the one that is losing electrons the anode, while the electrode that is gaining electrons, we call it the cathode. I'm going to run out of space. And we have a mnemonic that helps us out with that. And we say that this side is the ox, because oxidation is occurring at the anode. It is losing electrons. its oxidation number is climbing, as shown right down here. The aluminum went from 0 to +3. And on the right side, we say red cat, which means that reduction is happening at the cathode. Reduction, it is gaining electrons. And that is confirmed with below, where the nickel at +3 gained electrons for its oxidation number to drop down to 0. Now let's see if we have any answers that match this. Let me undo a lot of this drawing so we could examine the questions again. Actually, I've got an idea. Bring this to the forefront. Move the front. There it is. And what makes sense? Does number 1 make sense where it says oxidation and reduction both occur at the anode? No. One or the other. It says oxidation and reduction both happen at the cathode? Again, nope. Oxidation occurs at the anode. Remember, red cat and ox. Okay, anode oxidation seems to look good. Reduction occurs at the cathode. Red cat, looking good. Looks like number 3, but let's confirm. Oxidation occurs at the cathode? No. All right, it is choice 3. So why is the salt bridge so important? On the previous slide, I was suggesting to you very strongly that the electrons would flow through the wire to this side here. And you have to consider, if all the electrons are leaving the left half cell, eventually it's going to run out of negative charges and stop. So what the salt bridge provides is it provides an opportunity for ions that are developed by a salt in this solution. Ions, negative ions, to travel in this direction. And if they're negative ions, that means they're traveling with extra electrons to help resupply this side so that the circuit can be complete and it continue to run. So we have electrons running this way, stopping, reduction occurring, this electrode getting larger, but ions traveling in this direction to sort of resupply the left side cell so that the cell could continue to produce electricity spontaneously. Number 14, in a voltaic cell, voltaic, electricity being formed. Okay, in a voltaic cell, chemical energy is converted into, let's go ahead and underline, chemical energy is going to be converted. Now keep in mind, we do have a law of conservation of energy. Just always keep that in the back of your mind. Now, is this going to be converted into nuclear energy? Oh, no. Now, is it converted to electrical energy? Yep. And it's a voltaic cell, so it is going to happen spontaneously, all by itself. 15. When a voltaic cell operates, the ions move through the, let's take a look at this picture again, and where we have electrons traveling through the wire, we have ions traveling through the salt bridge. Now keep in mind, if in fact the anode was on the right side, everything would be in the opposite direction. So it is very important to identify which electrode is the supplier of electrons. So back to this question, when a voltaic cell operates, ions move through the salt bridge. Number 16. Given the balanced ionic equation representing the reaction in an operating voltaic cell, so this one's happening spontaneously, one of the electrodes is going to be more reactive than the other, losing electrons on table J. The question, the flow of electrons through the external circuit in this cell is from, so let's diagram this out. Okay, it's showing here zinc, uncombined zinc. I know it must be uncombined because it's a solid and it's only zinc, so it's oxidation number is 0. It is combining with copper ion, which is aqueous. So this suggests that, well, there might be some spectator ions here that are not being identified. And it's yielding zinc ions, aqueous. Again, it's probably combined with some spectator ion that's not being identified. And solid piece of copper. So there's your other electrode, and it has an oxidation number of 0. Let me actually draw this out. Here we might have our piece of zinc, and on this side our piece of copper, both solid. Here's a wire, and let's open up the circuit, put a voltmeter here, and there they are. Change the color, put it in a vessel, maybe like a beaker. Okay, and has to be in solution. Here we have our copper ions, and here we have our zinc ions. They are in solution. And what is missing? We are missing our salt bridge. Let's go ahead and put that in. There we go. Now we have a complete voltaic cell. The only thing we would have to do is close this switch right here. Now what is actually occurring? Well, we are going to witness electrons going from zinc through the wire once the switch is closed to the copper. The copper will get the electrons, and well, there's where the magic begins. So what do we need to see here? Well, I do need to remind you of this. Red cat and ox. Alright, so we do know that zinc is going to be losing electrons, and those electrons are going to be going to the copper. Alright, and we do know that when zinc loses the electrons, its oxidation number climbs, and that's oxidation. So we are going to have oxidation with the zinc, and we must have reduction at the cathode with the copper. And that actually brings us to our answer, number 3. Zinc is the anode, while copper is the cathode. Question 17. Which statement describes electrolysis? Well, electrolysis is similar to a voltaic cell in which they are both redox. They are both going to have electrons moving from one substance to another, one being oxidized, one being reduced. But there are some definite differences. Where in a voltaic cell, we are going to identify the flow of electrons by looking at the element that is higher on the activity table J, versus the lower one, and we know that electrons will move from the higher one to the lower one, and it will give off electricity. And, well, this isn't happening here. This is an electrolytic cell, and we're actually wanting it to do quite the opposite. We want the electrons to go from the least active to the more active. And the only way to make that happen is to add electricity into it. Now here is our example. Here we have a battery connected to an electrode that is pure silver and nickel. Well, silver is very low on that activity table, but we want to get the electrons to go from the silver to the nickel. So which of these choices suggest that? Chemical energy is used to produce electrical change? No. Chemical energy is used to produce a thermal change? This has nothing to do with heat. Electrical energy is used to produce a chemical change. Chemical change, we're forming ions. The substance now can behave differently. 3 looks good. Or thermal energy is used to produce a chemical change. Thermal has nothing to do with heat. The answer is 3.